All right, this is section 5.5. The rational root theorem. Now, we're going to talk about several different things today, but I want to talk about what the rational root theorem actually is. The rational root means your zeros, your answers to the polynomial, right? We've talked about all the different words that mean the same thing, and this is one of them. This finds you your answers to the polynomial, all right? So when I talk about the root theorem, that's what we're looking for. We're looking for our zeros. When you have a polynomial, so let's say I have y equals, I don't know, let's go with 6x to the fourth plus 5x to the third minus 2x squared plus 7x plus 4. That's a polynomial, right? How many solutions should there be to this beautiful polynomial? 4. How do you know that again? Quartic. Very good. The highest exponent. Very good. All right. So we know we have to find 4. All right. The way the rational root theorem is to find a couple possible roots or zeros. You take the factors of your last number, or the factors of the constant. So factors of the constant, and divide by the factors of your leading coefficient. That's supposed to be enough. Okay. All right. So in this case, factors of 4 are 1, 2, and 4. Everybody agree there? Factors of my leading coefficient, which is 6, are 1, 2, and good. Now, to find all of our possible zeros, and that's what we're going to call them, possible zeros, we've got to do all the combinations of what we just had. So we got to do plus and minus of everything. Let me move that up so you guys can see back here. So I'm going to start with 1. And I'm going to go 1 over 1, or plus and minus. 1 over 1 is 1. Then I'm going to go to the next one, 1 over 2. And then I have 1 over 3, or 1/3. And then I have 1 over 6. All right, so I have one of them done. Now, I like to cross out my 1, so I know I've already done that one. Now I'm going to move on to 2. I've got to go 2 over 1, so plus and minus 2. 2 over 2 is the same as 1, and don't I already have that? So do I need to write it down again? I'm going to go 2 over 3, so plus and minus 2/3. 2 over 6 is the same as 1/3. Thank you, and I already have that, so I don't need to write that one down. So now I'm done with my 2. I've got to go to 4. And again, all my combination, 4 over 1, or plus and minus 4. Then I go 4 over 2, which is 2. I already have that. 4 over 3, so plus and minus 4/3. And then 4 over 6, which is 2/3, and I already have that. So right now we have 2, 4, 6, 8, 10, 12, 14, 16 possible zeros. Does everybody agree with that statement? Okay, so 16 possible. Now here's where the rational root theorem comes in. You will take all of these possible zeros. We are going to plug them in, plug into polynomial to find true zeros. All right? So when I say true zeros, that means we're going to plug them into that polynomial and find out what actually gives us 0. Okay, now, here's the last little tidbit I want to tell you before we actually try one fully. Okay? When you plug it in, you only need to take the highest exponent minus 2, and that's the number you have to find. So in this case, out of all of those 16 possible, you got to find me 2. All right? Because the highest exponent is 4, you need to find 2 of them for it. All right? So here's going to be our first example. We're going to try it. You guys have totally got this. So we have example number 1. All right, for example number 1, which is going to cover your problems, which are only 10 through 16, right? Only. And let's start off with one that looks like this. And we're going to start off with an easy one. Let's say I have x to the third minus 4x plus 1. Starting off with super easy ones. So, first of all, let's look at that highest exponent. The highest exponent is 3, right? So that means if I take that highest exponent, subtract 2, I have to find at least one true 0. All right? Everybody understands that statement, correct? So now, go ahead, Hunter. Because we're going to find all but 2 of them. I always leave 2 because that's a quadratic, and you can solve that by the quadratic formula.
So whatever it is, we subtract by 2.
Correct. No matter what the highest exponent is, you got to find that many that's left. Okay?
Yep.
All right. So now, in this one, all the factors of our last number, our constant, is 1, right? All the factors of our leading coefficient is 1. So that means our possible zeros are plus and minus 1. So then the next step would be to plug each of those in and find out which one's the true 0. So we're going to start off by, let's start with the positive one. 1 to the third minus 4 times 1 plus 1. And actually, let's put the other one up here. Negative 1 to the third minus 4 times negative 1 plus 1. All right, Alyssa, will you put the positive 1 in for me? And you got it? Hunter volunteered to do the negative 1. Tell me what you guys get. You got 4, okay. You got negative 2. So neither of our possibles worked. If that happens, you're going to say no rational roots. What that means is that all of the solutions are imaginary, okay, or irrational. If there's no rational roots, they're imaginary or irrational. All right? Let's try another one. Same exact thing. I'm going to make it a little tougher, though. Example number 2. Let's go with, I got to find a really good one. I want a really, really good one. All right, let's go with 2x to the third minus x squared plus 2x plus 5. All right, and I want to find the rational roots. First we got to start with all possible ones. Okay, it is a cubic, so how many do we have to find, Hunter? 1. Very good. All right, all the factors of 5 are what? 1 and 5, good. And all the factors of 2? 1 and 2. All right. So our possible zeros are 1 over 1, or plus and minus 1, 1 over 2, plus and minus 1 half, 5 over 1, or plus and minus 5, and 5 over 2, plus and minus 5 halves. So this time we have 8 possible. And out of those 8 possible, we have to find 1, right? All right, so we have 2 times 1 to the third minus 1 squared plus 2 times 1 plus 5. Keep going. My buddy Derek. Yeah. All right. So let's say, Kaylee, you're going to do that one. 2 times negative 1 to the third minus negative 1 squared plus 2 times negative 1 plus 5. Marianne, will you get that one for me? Let's go 2 times positive 1 half to the third minus 1 half squared plus 2 times 1 half plus 5. Logan, you got that one for me? Okay. Then, of course, we're going to try 2 and then negative 1/2. But as soon as we find 1, we get to stop. You got 8? Okay. Yay! So since we only had to find 1, go ahead, Logan. What'd you get? Okay. That's fine. I'm more than happy to wait for Logan. Good. All right. So your first 4 problems in your homework, you're listing all of the possible zeros, and then you have to find me the actual true zeros out of your list. If there aren't any, you just say there's no rational roots. But you got to go through and plug them all in. Doesn't that sound exciting? All right. So let's move on to the next section in your homework. Sounds even more fun. All right. So one of the things we talked about when we were first talking about imaginary numbers is they have conjugates, right? They always have opposites. And any time we have I, we always have its opposite when we're solving for it, correct? So one thing before we get into this, if we have zeros that are either imaginary or irrational, then they always have a buddy. They are always going to be both the positive and negative. So today I'm going to ask you to find some polynomials like we did last week. Remember when I gave you the zeros and I asked you to put it in the box and multiply them? We're going to do the same thing, but we're now going to be imaginary and irrational. Okay, so if I give you a 0 that is 3i, that also means there is a 0 at negative 3i. If I tell you there's a 0 at square root 3, that means there's also a 0 at negative square root 3. They always work in partners, work in pairs. If I have a 0 at, let's say 4 plus 2i, that means I have another 0 at 4 minus 2i. Those are called conjugates of each other. Remember that word? Right? Okay, so next problem. Example number 3. This will cover your 18 through 20. Find all zeros given, let's say I tell you that we have 14 minus square root 2 and 7i. Well, we have zeros at 14 minus square root 2, but that means I also have a 0 at 14 plus square root 2. If I have a 0 at 7i, that means I also have another 0 at negative 7i. Thank you. I'm not sure who said that, but very good. That's all you have to do is list them all. So let's do one more kind of underneath the same example. Let's say you have zeros given to you as negative square root 2 and a 0 at 4 plus 2i. What are the other 2 zeros we need to list? Very good. Nice job, Orion. 4 minus 2i. Yeah, right? Okay. Now, what are we going to do with those? I'm so glad you asked. Here we go. Example number 4. You did ask. I totally heard you. Example number 4. Find the polynomial given x equals 3i. We're going to start with an easy one. So if you have a 0 or x equals 3i, that means x also has to equal negative 3i. Very good. So the first thing we do is we put them into factors. So we have x minus, if we move that over so it was a 0, x minus 3i. And if I move this one over, I'd have x plus 3i. All right, now we're going to multiply them together, which means we put this in the box. Very good. X minus 3i times x plus 3i. X times x is x squared. X times negative 3i is negative 3i x. X times 3i is positive 3i x. Negative 3i times positive 3i is negative 9i squared. First thing, what do I do with this I squared? I don't like him. Good. Excellent. We're going to cancel that, make that 9 positive. You'll notice my diagonal here, they cancel. So we get x squared plus 9. All right. So let's do another one. Example number 5. Oh, dream on, Hunter. Okay, this time I'm going to tell you x equals square root 3 and... No, let's go with 2i. All right, so if I have a square root 3, that also means I have to have a negative square root 3. And if I have 2i, that also means I have negative 2i. So here are our factors. The first one, if I move that over, I would have x minus square root 3. Maybe. All right, the second factor, if that was negative 3, I'd have x plus square root 3. For 2i, I would have x minus 2i, and we would have x plus 2i. Now, our goal is to multiply these all together and get out a beautiful quartic polynomial. So here's the trick to this. We're going to multiply the first two together. We're going to multiply the last two together, and then I'm going to ask you to multiply those together. All right? So our first little box we're going to do, x minus the square root of 3 times x plus the square root of 3. We get x squared. We get negative x square root 3. We get positive x square root 3. And negative square root 3 times positive square root 3 is negative square root 9, which is what? 3. Good. So our diagonal is going to cancel. First polynomial I have here is x squared minus 3. All right, let's do the next two. Here I'm going to multiply x minus 2i and x plus 2i. X times x is x squared. X times negative 2i is negative 2ix. X times 2i is 2ix. Negative 2i times positive 2i is negative 4i squared. What's special about that one? Yes, very good, Hunter. And what do you notice about this diagonal? Cancels. So we get x squared plus 4. Now what am I going to do with those two binomials? Yes, we're going to put them in the box and multiply those together. All right, last one. We have x squared minus 3 and x squared plus 4. Doesn't matter where they go. Very good. X squared times x squared is x to the 4th. X squared times negative 3 is negative 3x squared. X squared times 4 is 4x squared. Negative 3 times 4 is negative 12. And again, look at our beautiful diagonals going to add together, right? So we have x to the 4th plus 1x squared, or just x squared, minus 12. That is your polynomial from those 4 zeros. All right, so I'm going to ask that you only go through 24 and not 28 for me, okay? All right, so we'll add a little bit more tomorrow, but I want to make sure that you're going to do all of these to the best of your ability. Deal?
Yes, ma'am.
All right, thank you. And you still have a few more minutes, so let's go ahead and get started.